Hydraulic and Water Resources Engineering Laboratory presents Hydraulic Model Studies. I contend that unless the reliability of small-scale experiments is emphatically disproved, it is useless to spend vast sums of money on full-scale trials, which, after all, may be misdirected unless the ground is thoroughly cleared beforehand by an exhaustive investigation on a small scale. In hydraulic modeling, there are three kinds of similarities, namely geometric, kinematic, and dynamic similarity. Dynamic similarity implies corresponding forces in prototype and in the geometrically similar model must show a constant force-scale ratio Fr is equal to Fp divided by Fm. The requirement for geometrically similar hydraulic model is to ensure dynamic similarity, that is, all the forces in the model are reproduced at a constant ratio to those in the prototype. Typical forces acting on the fluid elements are viscous and gravitational forces. These are expressed as the ratios with inertial force to form dimensionless numbers. For example, Reynolds number is equal to inertial force divided by viscous force. Similarly, Froude number F is equal to inertial force divided by gravitational force. Froude number plays an important role in hydraulic modeling, particularly when the influence of gravity is important. Example, free surface flows. Very small Froude number means strong influence of gravitational force. Maintaining the Froude number same in the model and prototype is the important similarity criteria in modeling free surface flows. The Froude model law is Fr is equal to Vr divided by the square root of the product of Gr and Lr and is equal to 1. Herein, subscript R represents the corresponding ratios of the velocity, the acceleration due to gravity, and the characteristic length. Scale ratios for undistorted model are obtained. In the foregoing, G is same in model and prototype. That is, Gr is equal to 1. Length ratio Lr is equal to length of model divided by the corresponding length in the prototype. Area ratio is equal to Lr square. Velocity ratio is equal to square root of Lr. Time ratio is equal to square root of LR. Discharge ratio is equal to LR to the power 5 by 2. Simultaneous adherence of Froude and Reynolds laws in models of small scale is difficult. This requires a model fluid satisfying the relationship mu r divided by the product of rho r and gr is equal to LR. Therefore, simultaneous adherence of both Froude and Reynolds laws is difficult to implement in practice and will require a model as big as prototype. In free surface flows, the Froude model law is used for achieving dynamically similar water surface with the exception of stagnant or nearly stagnant water bodies. Maharashtra Irrigation Department has planned in Sangli district 2 lift irrigation projects, namely Takari Stage 1 and Stage 2. This is stated to be the biggest lift irrigation scheme in Asia. The water from Koyna river is planned to be diverted through a system of weir and approach channel to forebay of Takari Stage 1 and then lifted by pumping 63 meter using vertical turbine pumps into the forebay of Takari Stage 2. From here, it is again being lifted to be delivered to the subsequent stages. Total lift is 167 meter and total estimated irrigated area under this project is 25,986 hectares. It is customary to test the performance of the forebay and pump chambers by a hydraulic scale model study. Messrs. Kirloskar Brothers Limited, Pune, who manufacture, supply and erect these pumps, approached Hydraulic and Water Resources Engineering Laboratory of IIT Madras to conduct hydraulic scale model studies of these pump houses to study certain specific aspects of the hydraulic performance. They are flow separation zones, presence of surface and subsurface vortices, air entrainment, if any, and to suggest suitable remedial measures if required. Based on the availability of laboratory space, discharge capacity, model materials, accuracy required, and the cost, a model scale of 1:15 was chosen. The model discharge per pump is 1.983 liter per second, corresponding to prototype discharge of 6,220 meter cube per hour. Plan of Takari Stage 1. This shows the river, location of weir, approach channel, control gates and forebay with 3 compartments. Let us have a closer look. The approach channel is 260 meter long. There are 6 gates catering to 3 forebay compartments. There are 16 pump chambers of 5 plus 6 plus 5 configuration. This view shows the salient details of the middle compartment of the forebay, trash rack and trash rack pier and gates of 3 meter by 2 meter opening. This shows the longitudinal section of Takari stage 1. This shows the cross section of Takari stage 1. The salient features of the stage 1 are shown in the table. Plan of the model. This shows longitudinal and cross section of the model drawings. This shows the suction pipe and bell mouth assembly in the model. This consists of straight pipe, tapering portion, bowl and bell mouth.
This is the suction pipe. To make this suction pipe, and we made 4 parts for making this. There is a ball, taper part, then the tube and the flange. The first thing making this ball, we made a male and female forming die out of teak wood, and this is a piece from the perspex. We just cut it around, and the forming die just we have fixed here and heat up the perspex and pressed into this. So we got this type of ball, and we made two ball and joined together, two half we joined together and we got the ball. This is the first part. Then the second, the taper part, we made similar type of male and female die. You can see. And to to make this taper part, we just cut from it, making a template, and we cut a perspex again, heat up, and formed almost the similar type, formed here, and we got the taper part. The third part, the parallel tube. We got the parallel tube, and the last one, perspex flange. We just bore and made hole. This is the first part. Then we made a hole, bore in this, make 4 holes to suit the motor. And to suit this pipe for the taper, we just made this and make a taper so that it is fully tight. And this is the way. So you can see this is the type how we made the section pipe.
This chart shows the sequence of various activities involved in the model construction. Before the model construction is actually commenced, the layout is marked precisely on the level ground, and precise reference levels are marked and benchmarks located. Brickwork in cement mortar is then proceeded with. Water supply, pipeline and location of main control valve is then fixed along with an inlet tank of sufficient capacity. As the construction work of the walls of the model progressed, preparation of molds and casting of trash rack piers and slabs is made. Once when the model reaches the bed level, precise location of trash rack piers is determined. The brick and cement work is properly cured. The work of fixing of glass panels is taken up once when all trash rack piers are fully set in cement. Next, the work of painting, marking levels, plumbing and necessary electrical connections work are completed.
The different stages of the model are seen. The finished model is now ready for conducting the experiments. The experimental runs were made as per the given combination of the pumps P1 to P16 as shown in the table. The inlet valve is opened and the water is filled into the approach channel. Individual pumps are primed and the discharge is adjusted suitably. The water level is maintained at FRL by using gates, inlet and outlet flow control. The approach channel water level is monitored by using a drum type floating gauge and maintained at desired constant level. The paper confetti is used to trace the path of the fluid particles and to locate stagnation zone, if any, and surface vortices. The tests were conducted at 2F conditions, in other words, twice the normal discharge, to check for the possibility of the formation of surface and subsurface vortices in the pump chamber. The vertometer rotations were measured to calculate the swirl angle. Similarly, the water level is lowered to minimum water level and the experiments were repeated. The flow was measured over a calibrated 90-degree V notch. The calibration curve for 90-degree V notch is shown here. The results are summarized and a typical table is shown. The direction of the movement of the vertometer in individual pump chambers for given combination is indicated in the table. For all combinations, the swirl angle was within 3 degrees. No surface vortices and no air entrainment was noticed. Water in pump chamber was calm. It was observed that the presence of the slab at RL 536.6 has no adverse effect on the flow pattern in the pump chamber.
This figure shows the contour map of Thakari stage 2. The different color lines running on either side indicate contours of different ground levels. The minimum drawdown level at 595 meter and full reservoir level of 596 meter are also seen. The contour interval is 1 meter and the levels vary from 587 meter to 596 meter. This figure shows the proposed layout of the forebay and pump house. By superimposing this layout over the contour map, we can study the topography of the Takari Stage 2. Original proposal included the retention of central earth mound and by providing two channels with two berms of 1.5 meters and three slopes of 1.5:1. But as per the revised suggestion of Maharashtra Irrigation Department, this central portion is removed and the forebay level is maintained at 588.75. The central angle between the two pump houses is now 30 degrees. This view shows the earthwork excavation being carried out to remove the central mound. To improve the flow conditions at the entrance of the forebay, a ramp is provided. This shows the plan of the model. It consists of an inlet with diffuser pipe, reservoir, baffle wall, contours and forebay. The sections 11 to 88 correspond to the geometrical cross sections of the natural valley. The total size of the model is 9.14 meter by 4 meter. In this view, the plan and longitudinal and cross sections of the ramp provided at the entrance to the forebay are seen. The longitudinal section of the model is seen in this view. This shows the cross section of the model. The pumps are symmetrically located on both sides. This shows the typical pump chamber in the model. The intermediate slab is located at an elevation of 593 meters. The suction pipe is located at a distance of 86.67 millimeter from the dwarf wall. The dwarf wall, made of 12 mm thick glass, is provided for flow visualization. The suction pipe has the same dimension as that of model of stage 1, except that the clearance from the bottom of the pump chamber is 106.67 millimeter in this model. This table gives the salient dimensions of the model. The most sensitive and difficult part of constructing the model of stage 2 is to reproduce the geometrically similar cross sections of the natural approach channel to a desired accuracy. Typical cross sections of the approach channel are seen in this view. In points A, B, C, D in the cross section and the corresponding heights shown in the cross section represent the scaled down heights in the model. The dashed line and the finished line indicate the thickness of the plaster. In order to reproduce these cross sections, precise leveling is done. Six mm iron rods of predetermined heights are cut and vertically embedded into the channel bed to reproduce the desired cross sections. After the levels of the free ends of these rods are fixed individually, they are connected both in the vertical and horizontal directions such that the desired surface is generated in the model. This surface geometrically corresponds to that in the prototype. Free ends of these rods represent the levels of the points on the ground. Now you can see the whole skeleton in the model. The intermediate portion is filled by sand and other material to give a shape. The top surface is plastered to facilitate the smooth finishing subsequently. This view shows the process of installation of trash rack piers. Now you can see the completely finished model. Each color represents the contours at 1 meter interval and the lowest elevation is 587. The entrance channel is seen with its natural profile showing the contours marked thereon. You can now see the intermediate slab being introduced in the pump chamber. The model is now ready for the experiments. The experimental runs were made as per the given combination of pumps P1 to P16 as seen in the table. Water is first let into the model by opening the inlet valve. Water then passes through the diffuser into the approach channel. The water is maintained at any desired level suitably by adjusting the inflow and outflow. The pumps are individually operated by maintaining the water level at FRL. And measuring the discharge over the calibrated 90-degree V notch. Similarly, the water level is lowered to minimum water level and the experiments were repeated. This shows the close-up view of the water meter in action, which helps us in calculating the swirl angle. The fluorescein is used to check the presence of zones of separation, if any. The movement of fluorescein indicates the movement of water. The presence of surface or subsurface vortices can be observed. The woolen tuft are used for finding the direction of velocities. Results are summarized and a typical table is shown. The direction of the movement of water meter in individual pump chamber for given combination is indicated in the table. For all combinations, the swirl angle was within the permissible limit. No surface vortices and no air entrainment was noticed. Water in pump chamber was calm. It was observed that the presence of slab at RL 593 has no adverse effect in the flow pattern in the pump chamber.